Hi, I'm back again. So in the first lecture, we started talking about crystal diffraction, and we finish by introducing the structure factor. So today I'm going to continue from where we stopped last time. So let me get started. So, yeah, so if you remember, so we introduced structure factor called F. So with HKL indices. So the way we introduce HKL is that's a function of this change in your delta K, that is K minus K incident wave vector. So we found that's a sum of these all the positions of the basis atoms. So then we have something called the atomic form factor we introduced. So then we have this exponential term that's E minus I delta K dot RK. Remember delta K is that K minus K prime. So RK is the position of each basis atoms in the unit cell. So we know for the Bragg condition delta K is nothing but the GHKL, that's the reciprocal lattice vector. So it's in terms of this unit vectors. So then also if you know those indices HKL, so then if you take this dot product here, so UI, VI, WI are the indices or the coordinates of each atom in the basis. So that's the basic definition of the structure factor, FHKL. So if you write this one, write this one. So I equals 1 to n. N is the number of atoms in the basis of the unit cell. So we are going to use this one to calculate this structure factor for different crystal structures. That's the next few slides are just to calculate this structure factor for different crystal structures. So it's important to understand this structure factor describe how the atoms are arranged in the unit cell. The coordinates are given by these UVW coordinates. So for each atom. So we know that influences the intensity of the scattered beam. So the intensity of each diffraction spot or the peak is determined by this UVW coordinates. So also later you will find it will give you some selection rules. So what these crystal planes are allowed in the diffraction pattern. So these are the two important things to remember about structure factor. So let's start calculating the structure factor. So let's start. Before we do that one, there are some useful relationships you all should remember. So we know exponential, any odd number of this pi, right? E pi I or 3 pi or 5 pi I that is given by is equal to -1. Also in the integer numbers like 2 pi I, 4 pi I, 6 pi I, that's +1. So everybody should know that. So basically you are writing E n pi I as -1 to n if n is an integer number. So if because if n is positive, n is odd, you get -1. If n is even, you get +1. This is a general expression. So also we know E n pi I is equals to E minus n pi I. So using the Euler equation, you can verify that. Also, these two relationships are important. So EIX plus E minus IX is 2 cosine x. EIX minus E minus IX is 2 I times sine x. So this will be useful when we calculate the structure factor. First, let's start talking about simple cubic structure. Everybody remember simple cubic structure. You have these lattice points only at the ends. So this means you have only one lattice point for the unit cell, because each cell is shared by all other atoms, so you have only 1/8 of atoms, so then 8 of them you will get only 1 atom per unit cell. So then since you have only 1 atom in the unit cell, you can pick whatever the coordinates. So easiest one to pick is 0, 0, 0, right? So you can pick any point, so you get the same answer. Now, if you use this relationship, your ui, vi, wi are going to be 0, 0, 0. Then if you add this to, what do I get? So you have only 1. I goes from 1 to n, but n is 1, right? There's only 1 lattice point or 1 atom. So then you have f 2 pi. So 0 times h, 0, because ui, vi, wi are all zeros. Then you do this one, you get f. That means for always you get some finite value for hkl. So that's why for simple cubic lattice, all the reflections or diffraction from any lattice plane is allowed. So no matter what atom coordinates or planes you substitute into the structure factor equation, the simple cubic crystals solution is always non-zero. So you get always all the planes gives rise to your diffraction. That means all reflections are allowed for simple cubic. So sometimes we call this a primitive. Primitive structure means you have only 1 lattice point for the unit cell or 1 atom basis. So that's one thing to remember. If you have simple cubic structure, all the reflections are allowed. Now let's talk about lattice with a basis. So with basis more than 1 atom. So still you can consider simple cubic lattice with 2 atom basis. So that means your I goes from 1. So then we know the basis vectors for simple cubic lattice is a, all the same a values in x. These are unit vectors for x, y, z directions. So now again, if you do this one, since you have 2 atoms, you can pick the 2 atoms, one at just like before at 0, 0 position, other one, so any point you can pick, right, x, y, z. So now if I plug into this one, you get 2 terms, right? I equals 1, you get all this ui, vi, wi are going to be 0. Then you get fa for that atom. So it's atomic form factor for that atom A is, we call fa times ei, because it's all zeros. Second one, for the second atom at this position, fb 2 pi I, then this one will be x, ui is x, vi is y, wi is z. So if you do this one, you get this one. You can write this one, fa plus fb, this one. This is also true for any integers of hkl. Again, you will see this number is always finite, right? So that means this is also, you will get most of the reflections as your diffraction. So, but it's going to be very different if we have a body-centered structure. So, you know, if you have a body-centered lattice, you have 2 atoms in the basis, right? So you have, so all these cone atoms will give you 1. So because they all are going to be shared by 1/8, then 8 of them, you get 1. Then you have 1 in the middle. You have again 2 atom bases. So now if you write your 2 atoms in this equation, I goes from 1 to 2. In 1 you can write at 0. The second atom, it has to be in the middle, right? That is half, half, half position. So now if you use this equation, you get this f. You will assume both atoms are the same. So all these atoms are made up of the same kind of atoms. Or if it is, say, some potassium atom or something, so then all they have the same f value. So then you can write this structure factor. You have 2 terms, right? One coming from all zeros, you get 1. Other one comes, this your ui, vi, wi are going to be half, all this 0.5. So then you can see this 2 pi I divided by this 2, you get only pi I, right? So look at this one, 2 pi I, then this one has half, that 2 and 2 cancel, you get pi I h plus k plus L. Okay, so now this one is very, you have a little bit. Now, if this factor is, this h plus k plus L is even, so then this becomes positive one, right? So remember, so if this is even number, so then this we are 1, then 1 plus 1, you get 2, right? So that's why you get 2 times f. But if h plus k plus L is odd number, we know e to the power of this one is -1, then 1 minus 1 becomes 0. So that means if this is -1, so you get then this becomes 0, right? 1 minus 1, that's 0. So now you can see for this indices, the h scale represent the lattice planes, right? If the these are Miller indices, so if the sum of these 3 are even, you get this finite value, but if that is odd, you get 0. That means you will never get diffraction pattern from the planes that have this sum of these 3 indices are odd. So these are we call systematic absence of these reflections. That means if we have a Bcc structure, you only get reflections from things like that because the sum should be even. So here, this is, if you get this reflection, this is like plane of the family of planes, right? So typically we use simple bracket to represent a plane. So this curly bracket represent family of planes. So like 1, 1, 0 or 0, 1, 1 or 0, 0, yeah, see, 1, 0, 1, like that, any of that in that family. So, but you can see here, this is 1. If you take the sum of these 3, 1 plus 0 is 2. So that is even. Here, sum is 2. Here, sum is 4. This is sum is 6, sum 4. These are all allowed, right? But you cannot have reflection from 1, 1, 1 because then the sum is going to be 3. 3 is odd. So then you get 0 reflection. So it's very easy to remember. If you have a BC structure, you can only get reflections when the 3 indices, the sum of the 3 indices is even. So if they are odd, you don't get diffraction pattern from those planes. Okay, so next one is the face-centered cubic. So if you remember this face-centered, you have 8 atoms in the corners. So then at the center of each face atom, right? So then if you look at the number of atoms, you have 1 coming from all the corner atoms. So then from each plane, we get half of that, right? Because this middle one is shared by another plane, you get half of that. Then you have 6 of those planes. So then half times 6 is 3. 3 plus 1 coming from the corner, you have 4 atoms per unit cell. So then you can define those 4. First atom you can always put at 0, 0, 0, right? So the next one, the middle of one plane, that is 0 and half, half. So the other one you can put it another plane at the center, this half, 0, half. So other one, half, half, 0. So this is this one, right? So this is half, half, in the y-axis is 0. You can see all these 3 planes in the middle of the 3 planes. You don't have to consider both faces, only one plane, because opposite side is already considered, right? So you can see this 0, half, 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 0, half, or half, half, 0. These are the 4 atom positions. Now if you use this equation, you can see F. So first one, 0, 0, 1 will give you just 1. So here again we assume the same atomic form factor F, because we consider same atoms here. So then first one comes from this half, but 1 is 0, right? So if you consider this one, so H is going to be 0 because of this 0 here. You get again pi I because this half and there's 2 pi. This 2 cancel, you get this one. If you take the other plane, the middle one is missing 0, right? That's, you don't have K, you have pi I H plus L. third one you get H plus K. So that's the structure factor. Now, if you look at this one, you can see if all the this HKL, if they all are even, so then you get all these are added, you get 4 of them, right? 1 plus 1 plus 1, you get 4. But if any of them is mixed, that means you can have 2 even and 1 odd, or 2 odds and 1 even. If there's any mixed even or odd, then this term becomes -1, so that then it will cancel with another +1, then this one and the other -1 cancel, you get 0. So that means you can only get FCC reflections when HKL, all of them have to be odd or all of them have to be even. You cannot have odd and even mix. So for example, these are correct one, right? 2, 0, 0, you can 0 we consider as even. So you will have all even. So here 1, 1, 1, they're all odd. Here this is all even. Here this is all odd. Here this is all even. You cannot have like 2, 1, 0, because then 2 is even, 1 is odd, this mix, right? So that's not allowed. So please remember, if you have FCC structure, HKL all have to be even, no all have to be odd, no mixing. Okay, so now if you go to diamond structure, if you are familiar, diamond is nothing but like 2 FCC structures, so interpenetrated. You can think as is 2 lattices. So if you get 2 FCC lattices, you can just penetrate one into the another one, then you have the this diamond structure. So then you can think about 2 lattices, one with first lattice having this 4 atoms, right? So then you get just like before, because 1 FCC structure. So then same way you can get the second lattice, but now the second lattice, your atoms are actually along each axis is 1/4 of in each direction. You can see, so because this is interpenetrated, so that each atom is in going like 1/4 of each direction in diagonally. Is 1/4 along each direction, XYZ direction. So now if you write, that is for the first plane, just like regular FCC structure. For the second lattice, interpenetrated one, you can put the values like 1/4 of that. So if you add this one, because you get this additional term here, right? Please sub with this one. So now if you calculate the total structure factor, you have to add the 2, one for the regular FCC, other one is the interpenetrated along this quarter length interpenetration. So then you calculate this one, you will get reflections when you have, so this H plus K plus L have to be even, not only even, it has to be twice 2 times even number. So because this is 2 times even number, right? It's 2 times 2n. So, but if it is this 2 times even number plus 2 value, you don't get a reflection here. So you get weaker reflections when you have this H plus K plus L as some this 2 times n plus 1 value. This is actually odd value here, right? So you can see for FCC, we knew all the reflections come when HKL are all even or all odd, but when you have this diamond structure, so that's even, there are some reflections like this one, H plus KL is 4n plus 2. So there are some forbidden or unallowed reflections. So finally, I want to talk about the hexagonal closed pack structure. Everybody remember hexagonal structure here. So you have this hexagon, then you have these 3 atoms in the middle of this pyramid kind of structure. So here again, we can write our primitive vectors A1, A2, A3 this way. You have A1, A2, then A3 in the this direction. But remember, this A1 and A2, they are not orthogonal. So these are like 120-degree difference, right? The angle. So you can, in this case, you can, again, you have two atom bases. One atom is right at the, we can pick as this 0 origin. Other one is actually, so this 1/3 of one axis and 2/3 of other axis and half of the z axis. So this coordinates here, 1/3, 2/3, and half. So now if you plug into this equation, you have two terms, one coming from 1 here because the 0, other one is like this. So you can see now you get this F00 L becomes 0 when L is odd. So they have more unallowed reflections. So, but I think these are only you need to remember at this point simple cubic, BCC and FCC structures. But you know how to do for diamond and hexagonal closed pack structures also. Okay, but here is another special situation. Just think about this one as a BCC structure. Suppose this purple ball is also green. So then it is simple BCC structure, right? If you have a BCC structure, remember your the sum of the three should be odd, even, right? So if the sum is odd, you don't get any reflections. So, but that is when you have all these are same atoms. But this is a special structure. This is like we call the cesium iodide kind of structure. So this is not a really BCC structure actually. You can think this one as a really simple cubic structure with the basis of these two atoms. But if you think this one, the cesium iodide, so only difference is if they are all green atoms, they are regular BCC, then we should not get any reflection when the sum of the three coordinates are, three indices are odd. But in this structure, this F1 and F2 are different, right? Because this one is F1, this is F2. So then they don't cancel each other. If you have that situation, you can get reflections from even these ones. So here, if you look at this one, 1, 0, 0. If we add, what is the value? 1, right? That's odd. Here, 1 plus 1 plus 1, 3. That is also odd. Here, 2 plus 1 is 3, odd. But if this is a real BCC, you don't get these reflections. But here, since these are two different atoms, F1 and F2 are not same. So then they don't become 0. Then you can get even these peaks are allowed. So there's another simple situations for the FCC structure. Here FCC, but in this FCC structure, you have two different atoms. So this is more like sodium chloride structure, right? So if you have all same atoms, so then F is same, right? So F1, F2 are the same. So then remember your FCC, you can get reflections only when all indices should be even or all indices should be odd. So you cannot have mixed indices, right? But in this case, so these atoms can be different. So that means your F1 and F2 are not equal. So if you consider this potassium chloride and potassium bromide situation, so they both are FCC structures. But if you take the potassium bromide, in the potassium bromide, so this atomic form factor for potassium and bromide are different. That means they don't cancel because F minus F usually becomes 0, right? But here they are not different. So that means they don't, they are different, right? So that F minus F is no longer 0, Fa minus Fb, right? So since they are not canceling, you get reflections from all the FCC peaks. So that's what I think. If you have FCC peaks, you will get all the reflections, like you here 4, 2, 0, 3, 3, 1. So these are all even, all odd, all even, all odd. But if you take potassium chloride, you can see potassium and chlorine are equal. So that means, so some things can be, they can subtract out. So that's why you get only when all the indices are even. So you don't get reflections when all the indices are odd. So here in this one you get 420, 400, 222, all are even. But here you can get all odd and all even, because that atomic form factors are different. So that's important exercise to remember. So another important thing to remember is that the shape and dimension of the unit cell will determine the position of your Bragg peak, what angle or what position of your the dot. So what is in the unit cell, the atoms, they determine the intensity of the reflections. So that's the thing to remember. Okay, now if you consider sodium chloride, just like that one, so you have two atoms, like actually this is a FCC structure, right? Sodium chloride is a FCC structure. You have these 4 atoms, but they are different atoms, right? Sodium and chlorine. So that means you have atomic form factor, sodium and chlorine are different. Now, if you plug into that structure factor calculation, you get this all the 8 atoms, because you have each, you can have like 4 atom bases, but now each atom you can consider as sodium and chlorine. So that means you have sodium in these positions, 0, 0, then this 0, half positions, then chlorine ion at this half, 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 and 0, half, this. So then if you plug into that summation for the structure factor, you get 8 terms. So if you rearrange, you get this expression. So now you can see, if you have all HKL are even, this FHKL becomes 4 times FNA plus FCl. So this is never 0, right? This is a positive. So that's where you get the primary reflections. But when HKL are all odd, so you get this FHKLS 4 times FNA minus FCl. So remember this, these two numbers are different. So that means this is never 0, but this reflection is going to be less intense, because this is bigger than this one, right? So these are, we call the primary reflections. So these other ones are usually we call this superlattice reflection. They are much weaker. So if you again, this is FCC, if there's any mix in odd and even, you get 0 structure factor. That means no reflections. Here you will see this is the diffraction pattern coming from sodium chloride. You will see when you have this HKL all even, like 200, 220, they have this primary reflection. They have higher intensities, right? This one, this one, this one. These are all even. They have higher reflections. When you have all odd, like 111, 311, 331, they are superlattice reflection. Their intensities are much smaller, because you have this negative smaller, right? So please remember. So there's another example here. So, okay, this is the summary of what we talked so far. If you have a simple cubic structure, any HKL plane will give you reflections. BCC, you get only when the sum of the 3 are even. When they are odd, you don't get any reflection. FCC, all HKL should be all even or all odd. You cannot have any mixed indices. So sodium chloride, you get HKL. When it is even, you get the primary reflections. So, but you get this superlattice or weak reflections when FA is not equal to FB when everything is odd, because we can have both all even or all odd, but even all odd, so this is smaller, but we have to make sure they are not equal, right? So if they are equal, then they cancel each other. Diamond, so like I said, the HKL all even, but it should be twice an even number, like 4n. That means 2 times even number, or it should be all odd. The hexagonal closed bracket also you can calculate this any HKL except one case, this H plus 2K shouldn't be any 3 multiple of 3. Okay, so this is another thing to remember. Peak positions are determined by the shape and the size of unit cell. Peak intensities are determined by the atomic number and the position of your atoms in the unit cell. So later we'll find if we have a spectrum, the peak widths are determined by the instrument, right? So, and also later we'll talk about this, your crystal size, and if they have some strain or other imperfections, they can also increase the peak width. So peak intensities, like I said, so it mostly depend on, so intensity is scattered by individual atoms, that's a form factor, right? So then coming from the structure factor, that's basically how intensities are determined. Okay, so one more example about the superlative diffraction. So like I said, superlative diffraction reflects the periodicity of the lattice upon which the crystal structure is constructed using a basis of 2 or more different atoms, like sodium chloride, right? So that's how we created the superlatives, right? So sodium chloride is like FCC structure, but you have the sodium and chlorine, so they are different atoms. That's how you get the superlative reaction. So here we'll talk about one simple situation. So we have this cesium chloride. So actually cesium chloride looks like a Bcc structure, but it's a simple cubic with 2 atom bases. So we call that's not real, but we know real Bcc structures, right? So they have same atoms in this cone atoms and one at the very center of the crystal. So with different type of atom in one center, yeah. So here, this is what I was trying to talk about. One another thing to remember is in naturally occurring elements in your periodic table. So polonium is the only element that shows simple cubic structure. So there are a lot of like all this copper, silver, gold, they all are FCC structures, right? So iron can be both BCC and FCC depending on the temperature. So this is what I was trying to explain you. So if you take this polonium, these are simple cubic, real simple cubic structure. If you take this A2 structure, this is real BCC structure because all the atoms are same, but one at the center. This is B2 structure. This is not really a, it looks like a BC structure, but this is more like a simple cubic structure, but in your basis, you have this 2 atom basis. That's a cesium chloride structure. So if you take this structure, so if you take this unit cell, now I can, for this B2 structure, cesium chloride structure, I can write my atomic form factor, one at 1, then the other one at half, right? So this is always non-zero. So now, if you look at the intensity, so you will find if you take the 1, 0, 0 plane, so your intensity is given by this FA minus FB. So FA is one of these green ones, red is FB1. You can see your intensity is given by FA minus FB. So this is if FA and FB are same, they are 0, right? They cancel. But if they are different, you get some reflection, but they are weak. These are the superlattice reflection. But if you take 2, 0, 0, so in that case, you can calculate from that structure factor very easily. So you get FA plus FB. That means they are higher, right? They are adding up. So you get strong. We call this a fundamental diffraction. We already talked about that one for sodium chloride structure, right? So this means superlattice refraction reflects the periodicity of the simple cubic lattice, because this is really simple cubic, but the fundamental intensities shows the periodicity of a BCC lattice, because it has the formation of a BCC, but with 2 different atoms, not the real BCC structure. That's the difference here. So if you look at these peaks, you can see 1, 0, 0. You get very only 1, 0, 0 is weak one, right? You get, that's a weak peak, so it's a superlattice peak. But if you go to 1, 1, 0, so then you get strong peak. If you go to 1, 1, 1, again weak superlattice peak. So you can see how they are changing for different crystal lattices. Here you can see this is the ones that have this very bright ones. So this 1, 0, 0 or 1, 1, 0. Yeah, sorry, yeah, 1, 1, 0 is strong one, right? This one. Then you have 0, 2, 0, 0, 2, 0. That's also strong one. 1, 1, 0, strong one. So, but if you go to places like 1, 0, 0, so these are like this very tiny, very superlattice peak fringes here. So you can see these strong ones are here. It shows like fundamental, strong, fundamental, strong, fundamental, strong, these things. But these other ones weak. These are like this one, this one, this one, this one. These are superlattice. They are coming from this FA minus FP. These are so you need to understand how the superlattice diffraction is. So next I want to talk about this evolved sphere. So this is one way of looking at how the this diffraction happens in geometrical construction. So this is very simple. Suppose remember here we are talking about the reciprocal lattice here. This is not the real space. So reciprocal space, we are talking about the momentum space, right? So suppose this is my reciprocal lattice here. So because each point we can translate using that G vector, right? So now if I have my crystal, so if I represent crystal here, I have my incoming wave K0, then they get reflected by this K vector K. So then you get delta K here, right? So we know if you want to have Bragg reflection, so this delta K should be the G vector, right? So G vector is going from one point to another point. So to satisfy this one, what we have to do is, we draw a circle like this, in a way that geometrically. So what we do is we draw a sphere with your radius is actually 2 pi over lambda. We'll say, forget about 2 pi, it's 1 over lambda. You draw a circle with radius 1 over lambda, because we know lambda, right? So if you draw the circle, so from the this crystal position, that is your origin. So when you draw this circle, you find points where they intersect exactly that point. Look at these points, they are not intersected, right? But this point exactly intersected by this sphere. So that means that's the point that satisfies this delta K. So when you draw this one in the reciprocal space, such the origin is at the tip of the incident wave vector. So then any point of the reciprocal lattice which intersect that sphere represent the Lattice diffraction, right? So that point gives you that condition delta K that should be equal to G, because any point from one to other point can be represented by G vector, right? So here, if you go from here to here, that's the G vector. That satisfies the Bragg or Lattice condition. So because this point is not, right, because it's not in, but this one is almost correct. But we need to find, yeah, this point is perfectly fine, right? So this that's how we construct the Lattice, the evolved sphere. So here's another example. So if I have, like, this is my incident wave, so then I just draw a circle so that this is 1 over lambda, right? So basically, yeah. So if I draw with diameter 1 over lambda, so then this point I can describe as my delta G, right? From here to here. So that is delta K. That represent, in this case, 1, 1, 1. So then if I go to 2, 2, 2, so then in this one, so if I draw point here, so that intersect the point here. So that means this is my plane 1, 1, 1. So that is actually parallel to this. If I join this point and this point, so that is parallel to my 1, 1, 1 plane. Here again, if I draw this 2, 2, 2 plane, so this plane should be parallel if I connect from here to here. So this one and this one should be. So this is actually given by, ideally this is 2 pi over d. Remember, G, the length of your G is 2 pi over d, right? So here I didn't write 2 pi, this is 1 over d. So that's delta K or G. So here this is also delta K, because this is K prime. So this is delta K, right? So but delta K should be G. So G length is given by 2 pi over d. That's how you can get the geometrically what reflections are allowed using the evolved sphere. So here, this is, you can easily prove what we did, right? So here, if I draw with the radius 1 over lambda, so this is my delta K, that is 1 over d, or 2 pi over d ideally. So then this is the direction of your crystal planes here, like this. In this case, your crystal plane is this one here. So then this should be your G, right, or delta K. So if you do this, this is your definition of your Bragg law. So then here we can write sine theta is given by this G divided by, this is 2 over lambda, right? So from there you can calculate G is simply, this is ideally 2 pi over d. So I didn't write 2 pi here. You can easily prove, though, this how this construction is working. Only thing to remember is this is your incoming wave, this is your outgoing wave K prime, then K minus K prime is delta K. So delta K should be equal to your G. So length of G is given by 2 pi over d. So then you can get the by, if you connect these two, that is, you can get the crystal plane direction. Okay, so yeah, this shows you how to get this one. Draw a circle with diameter 2 over lambda or radius 1 over lambda. Construct a triangle with the diameter, hypotenuse is 1 over d. Diameter as the hypotenuse, and your distance is 1 over d. So then from here you can get the this right angle triangle that will give you the diffracted beam. So angle, yeah, then it will satisfy the Bragg equation. Okay, so also the Laue condition or the Bragg condition, G is delta K, K is K prime minus K, right? This is reflected one, this is the incoming one. So now if you square both sides, G squared equals K prime squared plus K squared minus 2 K dot K prime, right? But K squared and K prime squared, they are same because elastic scattering, then you get this equation. Just another way to write the Laue condition. 2k dot g plus g squared equal 0. This is same as the Bragg law. So then also you can write using this one your delta k times ai. So delta k is actually g, right? G times any of your, this is the real space primitive vectors. So when you multiply this one, we know that 2 pi times vi, right? So only this the Kronecker delta we talked about. So, okay. So here is one simple example. If I have this K incident wave, so this is my reflected or scattered wave. So this is delta K, right? That will be G for Laue condition, but we know that is, this is, if you calculate, you have 1, 2, 3, 4, and 1. This is 4, 1 plane, right? This reflection is coming from 4, 1 plane. So here's another example. So I have this incoming wave K. So then you have K prime. So this is my K vector, that should be G, right? So then you can find, if I take this one as my the origin in the real space, right? That's where we keep the crystal. But if you consider your origin in the reciprocal space as this one, so this one will give you have -2. If I measure from here, I have -2. This way -1, you get -2, -1 plane. Okay, so here's another example. If you do this one, you can see how the crystal plane should be, right? So like I said here, so this is the crystal plane. So K, this is K prime. So then if you take K prime minus K, if you draw minus K here, so this is delta K, right? That we call the capital K. So that is always perpendicular to your plane. So we know G vector is always perpendicular to the HKL planes in the real space. So the magnitude is given by, because this delta K is same as G, is given by 2 pi over that space in D. Okay, so now, so by simple geometry, you can calculate, if you know the plane Miller indices, the separation between two planes is given by this equation. 1 over d squared is given by this h squared. So this is a plane for HKL indices. So this is for this like orthorhombic structure, right? So your ABC are all non-equal, but all the angles are 90 degrees. So simple cubic, all these ABCs are equal, right? So then these all become just A. So but in orthogonal case, you can write as ABC are different. So always your 1 over d squared is this very simple to prove geometrically. 1 over d squared is given by h squared over a squared plus k squared over b squared plus l squared over c squared. In the case of cubic structure, so this is simply ABC are same as A. So now in the Bragg equation, remember what is the condition for diffraction? 2d sine theta equals n lambda. Then d is given by, for the simple cubic case, A divided by this one, right? 1 over d squared is A squared over this h squared k squared. Then you can write d as A over this one. So then d comes here. From here you can calculate your sine theta for each one. So, but if you go to different lattice structures, that separation is not easy to calculate. So these are the easy things to calculate, right? Orthogonal. So if it is simple cubic, this ABC are all equal. But if you go to like hexagonal, so that's also not too bad. Remember, you have these unit vectors. So by that you can easily calculate this one. But if you go to like triclinic structure, your 1 over d squared is this complicated formula here. So that's but we are only going to talk about orthogonal or simple cubic. Otherwise, it's non-cubic structures. This lattice spacing is very difficult to calculate. Let's do one quick example. So if I'm going to do 2 exercises, one for XRD pattern indexing and one for electron pattern indexing. So indexing means if you give me a diffraction pattern, so how can I assign these HKL values for each peak or each spot? That's the indexing means, right? So we'll only do it for a simple cubic, any cubic structure. So simple cubic with bases. So everybody remember this one. So this is the Bragg law. So then the space in between 2 planes are given by this equation. A is the lattice constant. So HKL other is the plane Miller indices, right? So now if I plug in this one 2 times, the D is this one, sine theta equals lambda. So if I calculate this sine squared theta over this one, if you square both sides, lambda squared over 4 squared. You can see this is a constant for a given crystal, right? Lambda is the wavelength of the X-ray and A is the lattice constant for a given crystal. That's constant, right? So that means we can write this sine squared theta over h plus h squared plus k squared plus L squared as a constant. So if you define this one also as some S, so we'll write this one as S, then I can write sine squared is theta equals lambda squared over 4 squared, and this one, so this we can write as S, right? That's a constant. So that means sine squared theta over some theta over theta 1 equals S over some different S1, right? So S is for a given plane. So this is for a different plane. So that means we only need to calculate the ratio between the squares of this sine squared. So that's the important thing to understand. When you give me diffraction pattern, what I'm going to do is just compare the ratios between the sine squared. So that will give you, because that ratio correspond to this your plane indices, right? So let's start with the, but before we do this one, so we have to keep track of these selection rules. Remember, if I have cubic lattice, if you have simple cubic primitive lattice, this h plus k squared del squared, that S value, right? That can be any of these, right? Except you cannot have 7 here, right? Because HKL can be any number 1, 2, 3 or 0. So then you can get all these numbers, 6, these things. But body centered, remember h plus k plus L is can be only, the sum should be even. So that means you are this h squared plus k squared plus L squared can be only these numbers, because all even means 0, 0, 2, right? So then you can get, yeah. So they all should be even numbers. So these are the numbers you can get. The sum should be, yeah, not each one. The sum should be even. So that means you can have 0, 0, 1, right? Because no, 0, 1, 1. Yeah, 0, 1, 1. So that means your sum is 2. So if you get the h squared plus k squared plus L squared, 1 squared plus, that is 2, right? So that way you can find only, you can get these numbers of this one, because of this one. If you take face centered, you know all HKL should be even, or all HKL should be, or you cannot have mixed one. So then if you take the sum, the h plus squared plus k squared plus L squared, they can be only these numbers. So what are the numbers you can have? You can have 2, 0, 0, right? So that's all even. So then if you square, then you get 4. Also you can have 1, 1, 1. yeah, that's all odd, right? So then if you square all of them, you get 3. 1, 1, 1, 2, 2, 0. This is 2, 2, 2, right? Yeah, 2 squared. Yeah, so like that you can have it. These things you need to remember. If you have a diamond structure, is also cubic structure, but diamond. So then these are the numbers. This is the one you need to remember to do this indexing. So here is some simple things. So if you do this one, so simple cubic, all these reflections are allowed, right? So for BCC, you can only have, because some should be even. So this is fine, 1, 1. So you can have 2, but you cannot have this one, right? Sum is 3. So this is BCC, only these ones are allowed. FCC, so these are not allowed because some, either all of them should be even or all of them should be odd. Here you have even and odd, you have even odd, but this is fine, right? All odd. So that's why you can see these are allowed. So diamond also, you can see this one. This SC is our sum. These are the numbers, right? So you can see what values are for this. So this S means this structure. Please remember, this is very important when you do this indexing. So, okay, let's start with some examples. Somebody gives me this spectrum. So they give me, they did the X-ray with X-ray coming from this aluminum target. So the lambda is 1.54 angstrom. So they give me the spectrum. So they give me these 2 theta values, right? So here, these are the 2 theta values. So what do? They ask me to tell me what are these reflections correspond to which plane. So what do? First, I need to make a table of these 2 theta values. So I put this peak, first peak is at 2 theta at 38, second peak 44. I just put like this. So then what I do is I need to calculate theta, right? I just take the half of that one. Then remember, what is important is the sine square theta, right? I need to take that ratio. Then I take the square of that one. Then I divide that sine square theta by my very first value, the minimum value. So then I'm going to keep multiplying that ratio until I see some pattern, like any of these kind of patterns. So then I can decide what is that structure is. So then after that, when you do that one, then very easy using 2d sine theta equals n lambda, you can find a value, right? Okay, so how do I do that? So now first I got 2 theta, then I take half of that and square that one. So that's this one. So now what I'm going to do is, this row I'm going to divide by this minimum one. So this 0.1083, right? So if divide by this one, you get 1. If I divide this by here, you get this number, this by that value. So everything is divided by this first minimum value. Then I get this value. This one I don't see any order, right? So this is very random. So then what I do is this one. So this is almost multiplied by 1, right? So now I'm going to multiply by 2. Then if I multiply by here, this becomes 2, 2, and see. Still I don't see any pattern, right? So now I'm going to multiply this by 3. 3 times this one. Then I get 3, see, 4, 8, 11, 12, 14, 16, 19, 20. That's exactly what we were looking for, right? If you remember. So this, for the FCC, what you get is 3, 4, 8, 11, 12, 16, 19, 20, like that. So now, if I didn't get another pattern, then I can go ahead and multiply by 4 until I see that pattern. So now, from here, I can stop. So I know that my structure is this FCC structure. So from here, then I can calculate my h squared plus k squared plus l, that these numbers, right? 3, 4, 8, 11, this one. So then how do you get HKL values? 3 FCC, we know they should be all even or all odd. So then how do I get these values? We know they are coming from 1, 1, 1. This is all even, all odd. So these are the numbers. So now I can go ahead and I know HKL then I can calculate d, right? So d is a divided by square root of a squared plus k squared plus l squared. So then if I know sine theta, so that I can calculate a. So this you can calculate. So from each value, so you get very consistent value for a. That's how you do the indexing for XRD pattern. So next I want to quickly talk about the electron diffraction. So electron diffraction is basically you have electron beam in your transmission electron microscope. So you have this sample with HKL planes. So this is a transmission electron. So then they will diffract through the sample. Then you get, if you have theta b, you get 2 theta diffraction, right? So then you find your diffraction spot on the screen or CCD camera. So then basically you measure this R HKL. So that's the distance to your diffraction pattern. So again, this one satisfy electrons, also satisfy the Bragg law, right? 2d sine theta equals first order n is 1. So now if you consider this theta is very small, then sine theta is theta, then I can write 2t d sine theta is lambda, 2 theta is lambda over dHKL, but also we know 2 theta is RHKL divided by this length L. So from sample to the screen length is L. So then 2 theta I can write lambda 2. That means I can write R times dHKL is lambda times L. You can see from here lambda and L are constant, right? So that means this the constant. So this is very similar to what we did for case of X-ray. We had that sine square theta is given by this lambda and what is that constant terms, right? So just like that, you have this sum multiple constant. So typically, if you look at electron diffraction, if you have a very single crystalline structure, you see very nice spots like that. So actually, then I'll show you how to, if you somebody give me this kind of structure, I need to index it. So what this spot coming from which plane. So, but if you have a polycrystalline sample, just like the lava pattern, right? So you have polycrystalline sample. So you know, actually it's more like the Debye technique. So you get this remember like one cone. So you get this circle, right? So then you will find, because you have reflections from this every crystalline directions, you get circles of these spots. So if you see something like that, we know that is polycrystalline sample. We already talked about that one in this Debye at the beginning. Right? So you can see these dots are not just individual dots. So these are a series of dots, but in a given circle. But if you have amorphous material, so there are no dots, but it shows some this fuzzy circles like that. So from that's definitely you can, by looking at the diffraction, you can tell what kind of diffraction or the crystalline structure you have. You can easily tell it's a single crystalline or polycrystalline or amorphous. So now if you want to index something, so here, so somebody gives me this diffraction pattern. So they tell me what is this distance. This is 1.10, this is 0.65. So then I have to index this one. I need to give what crystal planes corresponding to this pattern. So what do I do? First thing I do is I need to understand the symmetry. So if you have something, so there's something called the zone axis. So that is the direction of the most symmetric direction. So if you have this 1, 0, 0 direction as your zone axis, typically you have square symmetry. It's more like this one, what you have here. But if you have 1, 0, this is a direction. Remember this bracket tells you a direction. If you have a simple bracket, that tells you a plane. So if you have then you have families of planes and directions. So here, remember, these are the directions. If you have symmetry in the one direction, basically we are talking about hexagonal symmetries. So that's one thing to remember. Then from here we can easily tell you have symmetric axis is more like 1, 0, 0, right? Oh no, 1, 1, 0, because that's a rectangle. So these are two different ones, right? So another thing to remember is, so this allowed HKL. So typically, if you take square root of that one, for also the one thing too. So they tell me this is FCC lattice. So it's coming from FCC. That I need to know. So they have to tell me this FCC lattice. So then we know for FCC, you have to have all even or all odd. You cannot have mixed indices, right? Then from here we know what is square root of these values. These are square root of this is 3, square root of this 4. This is 4 plus 4, 8, square root of 8. This is HKL, right? So if you look at these values, these are like 1.73. This is 2. This is this value I calculated here. So now these are the two things to remember when you do the indexing. So first thing what I do is I just take the ratio between this 1.10 and 0.65. If I do that one, so 0.65 divided by 1.10, it's about 0.6. So now in this one, I just look at this ratio. If I take 0.3 over square root of 3 over square root of 8, that gives me 0.612. That's very close to this one, right? So that's a good candidate to start with. But later you will see if you take square root of 4 divided by square root of 11 and also square root of 4 divided by square root of 12. That's also very close, but we can show that they are not going to work. So we'll start with this one, square root of 3 over square root of 8. So if that is the case, so we just use this 1, 1, 1 and 2, 2, 0, right? So then one thing you need to understand is you should find a family of these planes. So because 1, 1, 1, another family is minus 1, 1, right? So then also you can minus 1, any of these. So when you multiply that by this 2, 2, 0, you should, if you take the dot product, right? So you should have 0. So that means they are 90 degrees, because we know this one, these are 90 degrees, right? Because we know this coming from square lattice. So we need to make sure from these ones you get that 0, because we know this becomes 0, right? So in this family, minus 1. So then if you multiply this one, dot product, what do you get? Minus 1 times 2, minus 2, 1 times 2 plus 2, and you add, it becomes 0. So that works fine, right? So then if you take any of other things, you cannot find any families to make this 90 degree. So dot product means you have to have 90 degrees, right? So cosine 90, 0. That's what we are trying to find here. So that means I can easily find these two are the right combination. So then I can easily find, so this is my 0, 0, 0. Then other one is 2, 2, 0, right? So if you multiply, you get 0. Then this will be minus 2, minus 2, 0. This is minus 1, 1. So you can easily find what are the combinations, because these are all coming from this 2, 0, 0 and sorry, 1, 1, 1 and 2, 2, 0. So then also you can find other combinations. So where you can get all these, if you multiply any of these, you get 0, right? So you can see how I can index these planes. So now, so if you want to find the zone axis for this crystal, so you just want to take the dot product of those two. So that means if I take, sorry, cross product, right? So if you take 2, 2, 0, and if you take, this is my 2, 2, 0, and if I take minus 1, 1, if you, because this is this vector and this vector, if I take the cross product, that's the axis perpendicular to that one, right? So actually, zone axis is, you can think about the reciprocal lattice, the reciprocal axis of the reciprocal lattice. Is more like a real space axis. So if you do that one, if you take the cross product of these 2 zeros, 2 0 and minus 1 1, these two, you get, this is my zone axis. So this is, otherwise this is 1 minus 1 2, right? So that is the zone axis. Okay, so there's another example. So this is actually shown already, the zone axis. So they are given like 0 0 1 as your zone axis. So that means anything you should have this, we know this should be 0. So then anything, if you take the dot product with this one, it should be 0, right? So then you can find all the positions you can get here. So this already you can index like we did before. So now if I measure the distance between these two, you get that is given as 10.96. So then if I take this is 0 2 0, right? Or 0 minus 2 0. So you know the distance between that one. So that distance is, if you measure from the origin, so half of that one. So that is 5.48. But that is coming from the 0 2 0. Remember, 0 2 0 is half of, because this, if you Miller indices, you have to have inverse, right? Then you take the inverse of that ratio. So then this is actually half of that 0 to 0, right? So that means this should be half of that the spacing a over 2. So that means your a becomes 2 divided by this one. So that is your lattice vector. Remember, this 0 2 0 is half of the 0 1 0, right? Because that's a half of the plane. So also each lattice you can translate like this, right? Because these are in the reciprocal space. So if this is 0, this is G1, G2, then you can go to the third one just by translating. That means this is G1 plus G2. You can see like this one you can make by adding this one and this one, right? So then you get this vector. So this is, so for example here, if this is 0, this is 2 0, this is 2 0 0, then vector sum is this one, right? If you add these two, you can see 0 plus 2 2, 2 plus 0 is 2, then 0 plus 0 is 0. You can create all the points once you find the origin and the at least 1 or 2 vectors. So that's what we did even here. If you find this one and this one, then you can calculate any of them just by vector sum, right? So you can see here, this is, if you add these two, this vector and this vector, you get this vector. That is 2 plus 2 minus 1 is 1, 1 plus 2 is 3, then 1 0 1. Here also, if you add this one and this one, you get this vector. You can see minus 2 minus 1 minus 3 minus 2 plus 1 is minus 1, 0 plus 1 is 1. If you get two of them, you can calculate everything. Okay, that's all I have. So this is the end of the second lecture. So my third lecture is going to be on magnetism. So thank you.